Chemistry in the atmosphere. It is important to read this chapter in the text as there is much background material. The composition of dry air at the sea level shows an interesting phenomenon. 78% of our atmosphere is nitrogen, 21% is oxygen, and argon is actually more in our atmosphere than carbon dioxide, 0.94 compared to 0.003%. The nitrogen cycle shows how nitrogen fixation converts the molecular nitrogen into nitrogen compounds. There are two primary ways that this happens. There's atmospheric fixation and industrial fixation. Atmospheric nitrogen is fixed in the following manner. Nitrogen reacts with oxygen to form nitric oxide, NO. This is often catalyzed by electrical energy like lightning. Nitric oxide reacts with oxygen, forming nitrogen dioxide, which in turn reacts with water to form nitrous acid and nitric acid. Industrial nitrogen fixation involves ammonia. Ammonia is made synthetically from nitrogen and hydrogen in the presence of a catalyst. The ammonia is oxidized to nitric acid and then reacted with more ammonia to form ammonium nitrate. Ammonium nitrate is a commercial fertilizer. The oxygen cycle is complex. Oxygen occurs in many forms. It is removed from the atmosphere, certainly by respiration, and photosynthesis is the primary way that oxygen is replenished into the atmosphere. Oxygen is also generated by the reaction of high-energy ultraviolet radiation with ozone. Let's look at the regions of the Earth's atmosphere. We live in the troposphere, the region of the atmosphere closest to Earth. 80% of the atmosphere is in the troposphere. Also important is the stratosphere, the next layer up. This is where the ozone layer is found. Above that is the mesosphere. And finally, the thermosphere, sometimes what we call outer space. The regions of the atmosphere are actually not defined in terms of altitude, but rather in terms of temperature. Notice the temperature variations. Let's look at some chemical reactions in the thermosphere. Solar radiation from solar flares generates lots of protons and electrons. These travel through space and react with monatomic oxygen, exciting the molecule. Protons react with nitrogen molecules and excite those. When oxygen, the excited oxygen atom, loses the energy, it appears as green and red light. And the nitrogen losing the extra energy appears as blue and violet light. These are what we call the northern lights that often are seen, especially during the winter. When spacecraft re-enter the atmosphere, an interesting phenomenon occurs. The monatomic oxygen reacts with nitric oxide in the thermosphere to generate excited NO2. The NO2 loses the energy, and this time the light is in the orange region of the visible spectrum. Very important is depletion of ozone in the stratosphere. Ozone is produced by ultraviolet light reacting with oxygen molecules, making monatomic oxygen. The monatomic oxygen reacts with diatomic oxygen to generate ozone. M is often a catalyst. Ozone is destroyed by the UV radiation reacting with ozone molecules, reverting them back to monatomic and diatomic oxygen. The monatomic oxygen can react with ozone to form two molecules of diatomic oxygen. This balance is what protects our population from ultraviolet radiation from outer space. It's a dynamic equilibrium, and if everything works correctly, there's a constant concentration of ozone in the stratosphere. Unfortunately, there is depletion of ozone in the stratosphere. Ozone is destroyed by CFCs, carbon-fluorine containing compounds. CFCs, like CFCl3, react with UV to liberate a chlorine atom. CF2Cl2 does the same thing. These chlorine atoms can react with oxygen, making ClO and O2. The ClO reacts with oxygen to make Cl and O2, and then net result is ozone is converted into diatomic oxygen. So it removes the ozone from the stratosphere. It is being catalyzed by the chlorine atoms. Where do the CFCs come from? Look at the pie chart. Air conditioning, both in autos and commercial air conditioning, commercial refrigeration, solvents from dry cleaners, foams and foam insulations, aerosols, all sources of CFCs. In this graph, we see that the ozone varies with latitude. Notice that when the chlorine monoxide increases, the ozone decreases. Polar stratospheric clouds provide a surface for this reaction. Hydrochloric acid reacts with this complex molecule to generate Cl2 and nitric acid. Spring sunlight reacts with Cl2 to make that monatomic chlorine. Remember that the monatomic chlorine reacts with ozone to make chlorine monoxide, which then uses another monatomic oxygen to make diatomic oxygen. The net result is that ozone is converted into diatomic oxygen. This graphic is really important. The purple is the depletion of ozone over the South Pole. Notice how it's changed, how it's grown over the years from 1980 to 2007. Even though this is 7 years ago, it's a very important phenomenon. It's leading to less ozone in various parts of the stratosphere. What may be implied from this is there may be an increase in problems related to too much exposure to ultraviolet light, such as cancers, skin cancers.